Hello and welcome everyone to my channel Code with Ease by Varsha. From today, we are starting a completely different series on time and space complexity. Let's quickly discuss what all we are going to cover as part of this playlist. So firstly, we'll talk of the introduction, what this space and time complexity mean, complete brief overview on that, the types, the different notations that we use. In fact, we are also going to discuss why do we use this. Next, we will cover on the generalization and optimization of time and space complexity. So a small example of this could be, suppose you are given a time complexity which is in the form of 2k plus n plus c plus log n, something like that, and this turns out to be the complexity of the given program or the logic. From here, how can you best represent this in the actual time complexity of that program is what we are going to discuss. How can we drop the constants? How can we drop the irrelevant terms? All of that we are going to cover. Then we will see a couple of examples or practice code snippets and determine the time and space complexity out of that. So we are going to take a couple of code snippets and then we are going to see how can we analyze the time and space complexity and do it live. How can we conclude the runtime complexity of those. Then we will discuss on the types. For example, you have log n runtimes. How do we calculate if a certain logic is going to have a runtime complexity of log n, recursive timelines, and also there is one more concept of the graph in which we are going to have all the complexities notations being arranged from. We are going to arrange all the complexity in increasing order, like the one which has the lowest and then the highest. So like best case to worst case kind of a thing, like constant space or constant notation is denoted by order of 1, and from here how do we progress to order of n square and then exponential complexity and so on. So we're going to take a look at that graph also. So the USP or the focus of this entire series is going to be on the third point and of course on the second point, because the best representation of a time complexity is what will help in the longer run. And since we're going to do loads of examples to determine actually the time and space complexity, I think that is going to be a good application of whatever we will be learning so far and do hands-on on several different kinds of code snippets. So that is the agenda for this entire series going to be. So this is the agenda for this series. What we are going to do is all the topics we are going to break it down into several different videos, like smaller chunks of videos, which is not going to be more than 10 minutes. And in that way, we are going to cover all the topics and curate this entire series. Examples part where we are going to discuss about the several code snippets, that also we are going to do it throughout the series. That also we are going to cover as different videos so that you can watch certain videos, take a pause, practice the questions, and then come back to the next video to see the solutions of that. So something like that we are going to do. So stay tuned and follow this series along so that you can have a good grasp over this time and space complexity topic. So without further ado, let's begin. So now we'll start with the introduction and the overview. What exactly space and time complexity mean? So as we can notice, time and space are two different entities. We often try to get confused when we talk of complexity and we say, okay, log n complexity, but you have to be specific. You have to ask, like, what complexity are you talking of? Are you talking of the time complexity or are you talking of the space complexity? And both of them have different meanings. So in general, if we talk of time and space complexity as one single unit, what do they mean? They're nothing but a metric. Okay, metric which is used to determine the efficiency of a certain program. Of a certain program or a certain algorithm, whatever logic you have written, that is what. Okay, so efficiency is the key over here. What is efficiency? As we have seen in schools, as we have learned in school, that efficiency is defined like work done per unit time. Okay, so if we talk of computer science language, it is something like how much time the particular algorithm or the program takes to complete the given work that it is assigned to. That is what is efficiency. So this time and space complexity are nothing but a way to judge, a way to determine how efficient your code is, how efficient your logic is. There are some related terms that we often use when we talk of time and space complexity, which we use interchangeably. The most famous one is the big O. Big O notations. We'll come to that, what notations mean. So big O is something we talk of interchangeably. We talk of runtime complexity. That is also one key term that we use. Then we talk of asymptotic runtimes or asymptotic notations. So all of these we use interchangeably whenever we talk of time complexity, space complexity in algorithms, data structure algorithm. But all of that means the same, like how efficient your program is. Express the efficiency of your program in terms of certain mathematical notation. That's it. So there is one misconception that people usually have with respect to time complexity. So one thing we understood is it is a metric. Time and space complexity both, they're the metrics which are used to determine the efficiency of a program. So efficiency is the key over here. What is the misconception? They think that, okay, if I have a program A and I have another program B, and program A is taking 10 seconds and program B is taking 100 seconds, so program A might be having a better time complexity than program B. Okay, but later when we dig deep, we analyze the code and we find that it is essentially the same set of code. There are 4 lines of code, same logic, 4 lines of code, and program B also same logic, but one is taking 10 seconds, another is taking 100 seconds. So it is wrong to conclude that the time that is taken by your program to run is equal to time complexity. No, it is wrong. And then your question might be, why this took 10 seconds and why this took 100 seconds? There can be a reason that the hardware of the computer on which these two programs were running are completely different. One is a very old version, one older generation of computer, and the second one is a newer generation of computer. And that is something which we have already seen, right? Some laptops, some computers run really slow when you're running your program, and then on the other hand, when you use a better computer, it is working really fast. Although it is the same program that you're running, you might observe that there is a difference, there's a lag in between. So hardware could be one issue. Another issue, it could be that maybe when you're running program A, you have given your input size. So let's say you have asked to do a sum of 10 integers in program A. Okay, sum of 10 integers, and you got the result in 10 seconds. Whereas when you're running program B, your friend is trying to run program B and he wants to experiment, and he has given, okay, I want to do a sum of 1000 integers, and then he got 100 seconds. So this is another reason that, you know, the size of the input which is given to run the program is different. So what we can conclude from here is time complexity is definitely not equal to the time taken by the program. Rather, what we can say is that it is the time taken to execute your logic. Okay, you execute your logic that you have with respect to the input size. This is the keyword over here. So with that being said, what is the baseline we have? The time complexity that we calculate depends on the input size. Input size is the primary factor that we have to consider over here. So it can be as simple as, if you have a program which takes in 10 inputs, 10 integers, 10 strings or whatever, and it executes and give you the result in 10 seconds. So now if I scale up and try to give it 1000 inputs, is it still going to give me the result in 10 seconds, or is it going to give me the result in 5 seconds, or is it going to give me the result in 100 seconds? Is what is being determined by time complexity of the algorithm that you've written. How the performance or the time taken of your algorithm scales up or scales down on the basis of whatever input that you have given to it. That is what is being told. That is what is being judged by the time complexity or the runtime complexity of your algorithm. Now, the other aspect that we have is space complexity. What is space complexity? Similar to time complexity only. What is the amount of space or memory that is occupied? Amount of space or memory that is going to be occupied when your program runs, again with respect to the input size. Now understand this very carefully, what we are trying to say. What is the amount of space or memory going to be occupied? When we talk of space or memory being occupied when our program runs, what is the most layman thing that we talk of when we write a program? Variables. We write int a equal to 5, int b equal to 10. What is this? These are nothing but this memory These variables are the reference variables. They're pointing to certain memory location, and that much memory is being occupied based on whatever the data type we have. Integer, short, byte, long, float, double, whatever it is. So if this amount of, so space complexity is a way to judge that, okay, you are having n number of variables in your program. What is the amount of space that it is being occupied as and when I scale up my input? So coming back to this example, if I am giving 10 inputs, let's say my memory being occupied is 5 MB. But the moment I make it like 1000 input, the amount of memory that is being occupied, it becomes humongous. Like it is now taking 50 MB. So just think of this, if this way it keeps on increasing, what is essentially happening is, based on the input that you are having, it is just the memory being occupied is exponentially increasing, and that is what is being determined by the space complexity. Many people try to confuse space complexity and auxiliary space. You might see it in many interview questions, lead code questions also. They try to confuse auxiliary space with space complexity, but then these two are not same. What is space complexity? Space complexity's formula, if I have to write, it is actually equal to auxiliary space plus your input space. Okay, now let me just clarify this again a bit. Input space or size, whatever. Auxiliary space is something like a temp array. You know, when we swap two integers, okay, we sometimes take a temporary variable, right? And then we just do the swapping. So now temp array is not dependent on your input size at all. This is like some extra intermediate storage kind of a thing which you are taking just for a time being, and this is not going to scale up with your input size. So that kind of a space is called auxiliary space, and that is, auxiliary space is not equal to space complexity again. Okay, now what is input space? Input space is something like you have a certain program to store 10 integers. So what is the input space again? So you have a program, there are 10 integers, okay, that is given to you as input. Now what you're doing is, you're taking another additional array and then you're storing whatever input is given to you in that additional array. So 10 integers are again stored over here in this array. And then after storing it in array, you're doing whatever computation you want to do. The problem over here is, let's say I give you 100 integers tomorrow as an input. You will take another array, you'll take a separate array to store the 100 integers again. If I give you 1000 integers, you'll take another array to store 1000 integers. So what we can see is, the input space is being increased exponentially as we are increasing the number of inputs. It is not like a one-time usage. Okay, think of like a hash map. You're storing something in the hash map and you keep on creating hash map for every input integer that you are having. You're keep on adding integers, entries to your hash map as and when your inputs are increasing. Today you have 10 integers, tomorrow you have 1000 integers. So additional space we are taking. In auxiliary space also we are taking additional space, that is like a temporary space, one time, and not dependent on the input size. But this one, input space, is something which is having a correlation with your inputs that you are giving to the program. So a combination of this plus this is what going to give you the space complexity. Hence, auxiliary space is not equal to space complexity. And to determine the space complexity, what is the dominant factor over here? The dominant factor over here is the input space. When I'm giving you 100 integers and then when I'm giving you 10,000 integers as the input, are you taking additional space to do the same computation logic, or are you not taking? And that is what is going to be determined by the space complexity. So that is a wrap on the overview of time and space complexity. So what are the things that we have to consider when we are calculating these things, and what are the things which we don't have to consider? What we have to consider is definitely the input size whenever we are calculating time and space complexity. And when it comes to what not to consider, when I say what not to consider, you are not going to consider the hardware where it is running. You're not going to consider the processors. You're not going to consider the OS. All of these are insignificant. When you're running the program, you cannot complain about these things. The only thing you can complain about is your input size. Okay. So with that, now the question is, what makes a good algorithm? Very intuitively, we can say something which takes less time and something which occupies, like saves space. It should not be like our previous example where as we are increasing the number of inputs, it is keeping on taking bigger and bigger arrays. It is something which shouldn't happen, because if it happens, what is going to be the downside of this? The end user, the clients, whoever is using your program, they are going to be impacted. Okay, one classic example is, we as a consumer, when we are trying to load any website, when we go to any website, how does it feel when the website doesn't load after 2 minutes? we are sitting and it is not loading. We say it's buffering, it's slow, some of the other problem. But actually in the backend, it all boils down to what algorithm is running in the backend. So always try to approach in that sense that, okay, whatever you're writing, eventually it is not going to be used by one user or 10 users at a time. Slowly it will scale up. Think of Amazon when the Prime Day sales and all happen. Think of billions of users are using it at the same time. So the kind of algorithm they write in the backend is going to impact big time when the number of users are increased, when they're scaled up in sale kind of a situation. So that is the goal of an algorithm, that always try to design something which is taking lesser time, trying to save you space. Okay. And when we talk of characteristics, what we can talk of is, we can say a good algorithm is something which should have high efficiency. A good algorithm is something which should have good amount of finiteness. When I say finiteness, it's like you should have a set number of lines of code in your this thing, so that it is not overburdening the memory. Okay. And third is correctness. This is like the crucial thing. I mean, you're writing an algorithm to find an element in an array, and if at the end, if you're not able to find the element only, there's no point, right? The accuracy or the correctness of the algorithm, like it should, given 100 integers or 1000 integers, at least it has to provide this correct input. It should not provide wrong input. Time and space is always a consideration, but the correctness of the algorithm is non-negotiable. The first thing that we have to do is correctness of the algorithm should be there. So this is what makes up a good algorithm. Time and space complexity is taken into consideration. These are the characteristics, and then what we should consider, what we shouldn't consider. Now the final part that we are going to talk of for today's session is the notations. Now we'll talk of asymptotic notations, what they are, how they help us in calculating the time and space complexity. We'll learn about those. So what do they help us in achieving asymptotic notation? They help us to determine how good your algorithm or an algorithm is in comparison to other algorithm. So when I was saying in the previous section that program A, program B, let's say your program A and B, two are running two different algorithms. So we want to compare if this algorithm's time complexity is better of A or is it better for B. How do we compare? To compare, we need certain benchmark, right? So that is why these notations have come into picture. What are those notations? The first notation is O notation, big O. By big O, it's written in capital, so big O notation. Then there is another notation called omega notation. This is the symbol for omega. And lastly, we have theta notation. Okay, this is big O, this is big omega, and this is big theta. Okay, mainly these are the three notations, and an equivalent of those also I'm going to write over here. So what each of these means: big O notation describes the upper bound of an algorithm. What it means: the maximum time the algorithm is going to take to run basically. What is going to be the maximum time this algorithm is going to take? Or this is also called as the worst case time complexity. Okay. So what is meant by this? These three, I've written like this because these three terms actually define what big O notation mean. An algorithm you have written, you want to understand how far can it go? Given a certain input size, how far can it go? Means what can be the worst case in which this algorithm is going to perform. So that needs to be notified, that needs to be understood by the big O notation. Upper bound, or what is the maximum time it can take, or what can be the worst case time complexity. For an example, you are given an array, okay, and you have to look for a target element in this array, like a linear search algorithm. What is the worst thing that can happen? You do not have the target in the target in this array. You do not have the target in the array, or your target is at the last location. This is the worst thing that can happen. Anything else that can happen in the worst case? No, right? Either your target itself is not there, or your target is at the end. So when that is the scenario that is happening, what is the problem with this kind of scenario? The problem with this is I have to iterate through the entire length of the array. If my length of the array is n, I have to iterate through the entire length of the array. And that is where we talk of something like big O of n, the worst case complexity, of this linear search algorithm is big O of n. Because if the target is not there, I kept on checking for every element until I reached the end of the array. Means I traverse the entire length of the array. Or if my element is at the last element of the array, I still have to traverse through the entire array. In that case also my time complexity became order of n. So this is what is denoted by the big O notation. Upper bound, maximum time that it can take, or the worst case. And remember, this big O notation is usually the most important notation and the most frequently asked or most frequently judged thing when you are writing an algorithm. Because think of this, when you are writing some logic, your end user, you don't know about the end user. Okay, you can have 100 today, you can have millions of users also tomorrow. So the end goal of this is what worse can happen with your algorithm that you've written. If I scale it up to this many number of users, what worse can happen? Okay, so always when you're writing an algorithm, that is something which you have to think. What is the worst case? Like in this case, we thought a target itself is not there in that. We are searching for something and that itself is not there. Okay, so that is the worst. Now, big omega, the second case. What is this? This is complete opposite of the big O. This is the lower bound. Lower bound of your algorithm's runtime, or the minimum time that it will take, or the best case time complexity. This is also something which comes up often. Minimum time means your algorithm is now taking, let's say, order of n. Okay, but it can take more than order of n also. So what is the best case? Again, the same example, linear search. Your element, what you are looking for, you got it in the first element itself. So you did not have to traverse the entire array. So it is something like constant. You didn't have to even traverse. You just looked up one element, found it is equal to target, and you returned. So that is the best case. So in ideal production scenarios, best case doesn't happen. It is always the worst case that we have to worry about. Hence, big O is more important. But still, we consider big omega notations also because we want to know what the best can happen and also what's the worst can happen, so that we can compare the trade-off between both. So big omega helps us to understand what is the best case. Big O helps to understand the worst case. Now finally we have theta. What can it be? It is the middle, like the average case. Okay, it is something between max and min. So this is the average case time complexity that it can take. And this is something which is rarely being considered when we are writing an algorithm, because if I have already considered what is the worst case, I don't have to worry about the average case complexity that much. But then when it comes to detailed designing of systems, we always weigh in all the different factors when we are writing the algorithm. So that is why it is important to know all the different scenarios with respect to that algorithm you are writing. So that if you are thinking in that approach, that is when you can write better algorithms. You can improve your algorithms. Okay. So that is all about the asymptotic notations overview. And with that, it is a wrap on today's session. In the upcoming sessions, we are going to cover rest of the topics like comparison of the runtimes. We are also going to determine this, how can we actually optimize, present optimized representation of time and space complexities. Then the graph of various different runtimes comparison we are going to do. So all of that we are going to cover. And of course, the main highlight, as I said, for this series is going to be the code snippets that we are going to practice live, where we will try to understand how are we analyzing the time and space complexity. So thank you so much for watching this video. Stay tuned for the rest of the videos on this series, and don't forget to subscribe to the channel so that you can never miss an update whenever we are posting a new video. Thank you so much.